For my project, I used Mathematica to model orbital mechanics, looking at the motion of the Earth, Moon, and satellites. We examine Kepler's laws and the behavior of an Earth-Moon system, and apply our knowledge to sending crafts to the Moon. We will assume coplanar circular planetary orbits. It all boils down to my favorite equation, F equals ma, where if we have two masses, 1 and 2, then the force between them is equal to the gravitational constant times their masses over the distance cubed along the vector that connects the two bodies. We can now break up our motion into x and y components and use our force equations to get acceleration. To make a numerical solver, we break our second-order equation in acceleration to two first-order equations. Thus, to describe a body in 2D, 4 state variables are needed. 2 for x and y position, and 2 for x and y velocity. So we make a state vector x and a state vector x prime to completely describe our system. Now we create a numerical solver that performs the Runge-Kutta method on our state vector, which says the values of our state vector after one time step are determined by the present state plus the weighted average of 4 increments denoted by k. The equations for k are given below, but in a nutshell they represent the increments based on the slopes at the beginning, middle, and end of our time step interval. Note that Euler's method takes into account only k1, the slope at the beginning of the interval. So now we can verify the accuracy of our numerical solver at modeling orbits by seeing how well it follows Kepler's laws. Kepler's first law states that the orbits of the planets are ellipses, with the Sun at one focus of that ellipse. We use the following state vector in a reference frame where the Earth is at the origin. Because we only want to examine the Earth and a satellite, we place the Moon far away with 0 mass. The satellite starts out about 42,000 kilometers away with an upward velocity of 2,000 meters per second. Our Runge-Kutta method takes these initial conditions and progresses them through time. Let's see if our orbit follows Kepler's first law. Remember that we define the Earth as the origin. We say that 2a is the maximum x distance and 2b is the maximum y. Where they intersect is the center of our ellipse. Going through the xy coordinates of our orbits, we obtain the following values for a and b. The distance from center to focus is c, where c squared is equal to a squared minus b squared. We obtain that c is equal to 1.54 times 10 to the 7th meters. We subtract c from the x value at the center of our ellipse to find the location of our focus. Our focus is at an x value of 0.0424 meters, whereas the Earth is at 0. There is some error, but in terms of space, hey, what's 4 centimeters? So yes, the Earth does lie at one of the foci of our elliptical orbit. Now we move on to Kepler's second law that states that the line joining a satellite and the fixed Earth sweeps out equal areas in equal times as the object follows its orbit. We can indeed observe that the orbital speed is not constant along the ellipse. To find the area between each time step, we take advantage of the fact that dA is equal to r dr d theta. Integrating then, we get that the change in area is equal to r squared over 2 times the change in angle. Given two vectors v1 and v2, and the angle theta between them, the dot product of the two position vectors is equal to the magnitude of the first one times the magnitude of the second one times the cosine of the angle between them. If we make a plot of the change in area associated with each time step, we see a constant, meaning that yes, our numerical solver follows the second Kepler's law, where equal times sweep out equal areas. Finally, let's test Kepler's third law, that says the ratio of the squares of the orbital periods of two objects is equal to the ratio of the cubes of their semi-major axis. To confirm the third law, we create a second satellite at twice the distance with the same initial velocity. And Runge-Kutta gives us the orbits based on these initial conditions. We get the following values for orbital period and semi-major axis. And taking the third law ratios, we see that our orbits are valid. Now that we've verified Kepler's laws, let's move on to simulating the Earth and Moon. Using an arbitrary origin, we write the force equations for the Earth and Moon, where just plain r is the distance between the two bodies. Recall Newton's third laws and action-reaction pairs. We write the individual force equations for the Earth and Moon, divide by mass, and subtract. The final result shows we can turn our two-body system into two independent one-body systems of reduced mass around the original Earth-Moon center of mass. Now we just have to find the orbital velocities of the Earth and Moon in this reduced system. Because our system has only internal attraction forces, we know that total momentum is a constant zero, and thus that the center of mass is stationary. To have two unknowns with two equations, we can also write our centripetal force equation in terms of distance from the center of mass, along with the equation for gravitational attraction. Solving the system of equations, we can determine the Earth-Moon orbital velocities. We run Runge-Kutta to map the orbits, and observe that the Earth and Moon have the same angular velocities. So if we make a rotating reference frame, by applying a backwards rotation matrix on each point dependent on time, then the Earth and Moon appear to be stationary. Note that because our magnitudes are so large, we have non-dimensionalized in terms of the Earth's radius. If we model an Earth satellite without the rotating coordinates, we would get this image, where the satellite is red and the Earth is blue. We can gain much more information if we use rotating coordinates, as shown here. So now let's add slight disturbances to orbital velocity and see what happens to the satellite's path. A large enough disturbance will send the satellite towards the Moon. But this random guess and check method is unlikely to put us on a trajectory that will let us enter orbit. Instead, we start at the Moon and go backwards to the Earth, and identify where we have an Earth capture point, at which our trajectory is tangential to an Earth orbit of lower velocity. Here, we can apply a rocket burn to slower velocity and re-enter Earth orbit. Let us say we want to enter an orbit at twice the Earth's radius. Our parking conditions are satisfied about 3.2 days into our trajectory. Now we use the image theorem to reverse our trajectory to go from the Earth to the Moon. The theorem states that, in general, a trajectory cannot be flown in reverse back to its original point. However, we can fly its image. That is, we take our final parking point from before as our new starting condition, and then take its image by flipping the signs of its y position and x velocity. Using Runge-Kutta to determine this image trajectory, we see that we've created a means of going to the Moon and back using a slingshot. Ultimately, we created a numerical solver that takes any given set of initial conditions and returns accurate trajectories in a convenient reference frame based on the system's gravitational pair interactions. Using these principles, we can model really any system. So now, like with space, the possibilities are endless.